Hello chemists, this is Ms. Placino and you're watching lesson 3.3 on periodic trends. This is the follow-up lesson for 3.2 where we introduce the trends of atomic radius and ionic radius, and we're going to wrap up that discussion today. So a couple of goals for the lesson. We're going to be able to provide definitions of first ionization energy and electronegativity. Those are the two trends we're discussing today. Recall the trend for first ionization energy, be able to explain why that trend is observed. We're also going to do the same two things for electronegativity. What is the trend and why is it observed? So lots to do today. Let's get into the lesson. Today we're really going to be focusing on the valence electrons, and this is a term that has come up a couple of times by this point in the semester. So remember, our valence electrons are the ones in the outermost shell of an atom, and they're the ones that are primarily responsible for the properties of that element. Again, we're going to be focusing on the S and P blocks of the periodic table, so really groups 1 and 2, and then 13 through 18. And we know as we go across a period, we're adding in an additional electron, so we'll see 1 valence electron in group 1, 2 in group 2, 3 in group 13, 4, 5, etc., all the way to 8 in our group 18 nonmetals. Doesn't matter if you drop down to the next period. Within the same group, you end up with the same number of valence electrons. They're just an extra energy level away. So we'll keep that in mind as we talk about first ionization energy and electronegativity. So first, let's talk about formation of an ion. Well, for starters, what is one? Yeah, an ion is basically an atom with a charge. How did we form an ion? Well, you've got two options. You can either gain electrons or you can lose electrons. Those are the only two ways to become an ion. We cannot gain or lose protons. As you might imagine, ionization energy has something to do with how much energy is either released or required when an ion is formed. So let's kind of look at that in a little bit more detail. When we're talking about first ionization energy, we're talking about the production of a cation. How much energy do we have to put into a neutral atom? Basically to pull an electron away. Now, even if an element wants to get rid of an electron, they're still attracted to the nucleus, so we're going to have to put some energy in to pull one off. So first ionization energy really just is the amount of energy in terms of kilojoules per mole. Kilojoule is a unit of energy, mole is a unit of quantity in chemistry. Don't stress about it now, it will be coming up in more detail in future units. But the amount of energy required to remove the outermost electron from a neutral atom. We're not looking at removing an inner core electron, we're talking about pulling off a valence electron. Valence electrons should be the easiest to remove. They're the ones that are farthest away from the nucleus, so they have the least kind of feeling of that attraction to the nucleus due to the distance. So our first ionization energy trend. What I'd like you to do in your notes, there is a kind of like a cutaway of the periodic table. I want you to fill it out with the element symbol and its first ionization energy. And you can use table S in the periodic table to look them up. What we're going to do is try to observe the trend down a group. Does ionization energy increase or decrease as we start at the top of the group and work our way down? And we're going to kind of answer that same question for across a period. Most importantly, we're going to try to explain why this is observed. So pause the video, start to fill out your periodic table cutaway with some ionization energies. All right, so this is kind of just an overall picture of what first ionization energy would look like. We can kind of see as we go down a group, we've got decreases in first ionization energy. And as we make our way across a period, it does kind of bounce up and down a little, but there's a general increase in first ionization energy. As always, the more difficult aspect is trying to explain why this is observed. So let's go ahead and start to fill this out. You probably have this done already. Hydrogen, 312, lithium, 520, beryllium, 900 kilojoules per mole, boron, carbon, so on and so forth. We'll just fill it out. Okay. So as we go from the top to the bottom of a group, we see first ionization energy decreasing. And that's the energy required to remove the outermost electron. Why is it easier to remove an electron from, let's say, potassium than it is lithium? Think about the size of those atoms. We know as we go down a group, atomic radius increases. So those valence electrons are further and further away from the nucleus. Since they're further away from the nucleus, they're not as attracted to it. So it's going to require less energy to pick one off. So down a group decreases. The valence electrons are less attracted to the nucleus because they're further away. Generally speaking, as we go across a period, we see an increase in first ionization energy. Why? And try to tie it back to atomic radius. Well, as we go from left to right across a period, we know that those atoms are becoming smaller and smaller and smaller. As they get smaller, those valence electrons are pulled more tightly to the nucleus. They're more attracted to it, or attracted more strongly to it. So it's going to require more energy to try to pull them away. We've added the proton, making the nucleus more positively charged, more attractive, or stronger. They're still all in the second energy level. So it's just going to pull those electrons in, and it's going to require a lot of energy to remove a valence electron. Now you might be looking at this, especially if I get that red line out of the way, and saying, well, wait a second, we've got kind of a big difference there. It's almost 100 kilojoules difference in energy, and it's supposed to be going up as we make our way across. Why is it going down? And for the time being, I will just tell you that is a really good question, and I bet you already can answer it on your own. Definitely worth something worth looking into. Before we move into practice problems, I just really want to drive home this relationship between atomic radius and first ionization energy. It's really important that you are able to connect the trends. We'll look at those two. Well, we know that sodium has a very large atomic radius. Chlorine has a small atomic radius. The first ionization energy for sodium is, where did it go? 496 kilojoules per mole. And for chlorine, it is many times as high, 1,251 kilojoules per mole. Now basically, it's an inverse relationship. The larger the atomic radius, the smaller the first ionization energy is going to be. The smaller the atomic radius, the larger the first ionization energy is going to be. Really make that connection between the two trends. We're back over into the practice problems, just like with the previous lesson. Let's do all of question A. And again, don't just turn to table S and look up the numerical values of these elements. Try to apply the trend based on the location of these two elements. Which one's going to have the lower ionization energy? Okay, let's review these. So we've got argon and krypton. They're in the same vertical column. Argon is above krypton. We know as we go down a group, ionization energy decreases. We're looking for the one with a lower ionization energy. Krypton should require less energy to remove the outermost electron than argon. If we take a look at rubidium and strontium, they are right next to each other. Rubidium comes first, then strontium. As we make our way from left to right across the periodic table, we see increases in first ionization energy. Therefore, rubidium must have the lower of the two ionization energies. We've got beryllium, and it's kind of like kitty corner from sodium. Okay, we know as we go down a group, ionization energy is lower, and as we go from right to left, ionization energy is lower. So sodium's both below and to the left of beryllium. It's got to have the lower ionization energy. And finally, we've got rubidium and bromine. Kind of the same idea. We have gone down to the next period. When we've gone to the left, many groups, this is group 17, rubidium is group 1. So rubidium should have a substantially lower first ionization energy. Rubidium should have a substantially lower first ionization energy than bromine. Let's make it a little bit more complicated. Pause the video, tackle questions 3A and 3B. Okay, so I don't have to flip back and forth between this page and the periodic table. I just kind of wrote out the essential information. So for question 3A, we want to go from highest to lowest ionization energy. And if you found those 4 elements, you notice that they're all in the same group, group 17. We know that ionization energy decreases going down a group. So the element at the top of the group, in this case F, fluorine, has the highest ionization energy, then chlorine, then bromine, and then iodine. So highest to lowest. Question 3B talks about 4 elements that are in the same vertical column. So I know I've got more there than we need, but we're going to have our highest ionization energies towards the right side of the periodic table. So there's no neon, there's no fluorine, there's no oxygen. Carbon should have the greatest of, nitrogen should have the greatest of the 4 listed. Then carbon. Then boron, and Be, beryllium, should have the lowest ionization energy. Just like last time, questions C and D are a little bit more involved, in particular question C. So I would say try those out on your own and check the answer key. Let's get back to the notes. The last trend that we're going to focus on is electronegativity. So we've kind of represented the trends in a couple of different ways. So for atomic radius, I had you plot a whole bunch of atomic radii versus their atomic number. For electronegativity, we kind of use that cutaway of the periodic table to just fill out the numbers. I want you to try to just use table S to deduce this without necessarily graphing or writing any additional information down. So let's talk about what happens to electronegativity as you go down a group and across a period. So you should have table S in front of you. Find electronegativity. You'll notice that it's unitless. We'll talk about why that is in just a minute. As you kind of make your way, we'll start with across a period. I think that's easier. What seems to happen to your electronegativities? Yeah, if I look at lithium, beryllium, all the way over to fluorine, I'll see that across a period, electronegativity increases. Until you get to group 18, then there's just a little dash. We'll figure that out later. What about down in group? I'm going to look at element 3, lithium, 11, sodium, 19, potassium. I go from 1 to 0.9 to 0.8. If I go to rubidium, I can find that one too, number 37. It's also 0.8. We're seeing a general decrease down the group. Okay. So that's the trend that we observe for electronegativity. Decreasing down a group, increasing across the period. What do you notice about the electronegativity values for most of the group 18 elements? Helium's group 18, there is a dash. Neon, also group 18, dash. Argon, group 18, dash. Krypton, number 36, group 18, also a dash. These are not listed or not provided. And everything else is, so I don't think this is just missing information. So maybe they don't have an EN value. It's a clue into what electronegativity is actually a measure of. What do we know about the reactivity of group 18 elements, our noble gases? Yeah, they're basically non-reactive. The chemical term for that is inert. Does not react. Okay, so we are observing a trend that seems to get stronger in non-metals than it does metals. And we know that elements that don't react, like the noble gases, don't have an electronegativity value. It's got to be able to react and form bonds. Must be, because we know group 18 elements don't react and tend not to form bonds. So this has to be something that to do with reacting and forming bonds. And do metals or nonmetals have higher electronegativity values? Well, we know the metals are on like the right side of the table, the left side of the table, excuse me. And as we make our way to the right, it gets increasing our electronegativity values. So nonmetals have the higher electronegativity values. All right, so what could electronegativity be measuring? I'll give you a hint. We're working our way there. Think about tug of war. What might be kind of like the rope, if you will, in this tug of war game? We know group 18 elements do not participate because they do not form bonds. It turns out that rope is a pair of electrons. So electronegativity is the ability of an atom in a compound. So this means two atoms bonded together. I'll be more specific, two different atoms bonded together to attract electrons from another atom in a compound. So you have two atoms that are bonded to one another, and who is winning this tug of war over a pair of electrons? We know that our nonmetals are better at doing this than our metals. Metals tend not to attract electrons. They tend to lose electrons. And electronegativity has no unit because this is an arbitrary scale. Scientists came up with this. They're not really measuring anything. They were just looking at how electrons are being shared between atoms when they're bonded to one another. It's based on a scale of 4.0. So our most electronegative element is going to be furthest to the right, furthest towards the top, leaving group 18 out of the discussion. So hopefully you're zeroing in on fluorine, which has been assigned an electronegativity value of 4.0. And as you start to get further away from fluorine, you start to see lower and lower electronegativity values. Again, we're just having that attraction between a stronger nucleus, a smaller atom generally, pulling the electrons towards itself, possibly from a larger atom with a weaker nucleus. But it has to be in a compound. You have to have those pair of electrons shared between two atoms. We are back into the practice problems. Go ahead, try out question 2A through D. Again, compare locations on the periodic table. Do not just look up answers on table S. All right, let's check these out. We want to circle the atom with the greater electronegativity. So that's going to mean the ones that are further to the right and closer to the top of the periodic table. Calcium and gallium are in the same period. Calcium is to the right, to the left of gallium. So the greater electronegativity is going to be gallium. It's closer to fluorine. If we look at bromine and arsenic, we've got arsenic, selenium, and bromine all within the same period of the periodic table. The greater electronegativity is going to be, in this case, bromine, because it's farther to the right. Lithium and oxygen. Lithium is, let's see, my mistake, let's write those in the same horizontal line. Lithium is in group 1 of period 2. Oxygen is in group 16 of period 2. Oxygen is obviously further to the right, closer to fluorine. It's going to have the higher electronegativity. We've got barium, which is right below strontium on the periodic table. So SRBA. We know as we go down a group, electronegativity decreases. So strontium should have a higher electronegativity than barium. Really try to get used to using the locations on the periodic table to determine which element is going to have a greater or lesser electronegativity. Do not just look things up on table S. And finally, to finish up with the practice problems, let's take a look at questions 4A and B, then we'll recap the trends. So pause it, try it out. All right, if we take a look at question 3a, those four elements are all in period 3. So here they are in order from left to right. We want to go from lowest to highest electronegativity. We know electronegativity increases across a period from left to right. So magnesium is the leftmost of the elements we've got listed. It will have the lowest. Then aluminum. Then looks like sulfur. And chlorine should be the most electronegative of that group of elements. In 4b, sodium, potassium, lithium, and rubidium are all in the same vertical column. They're in the same group. Electronegativity decreases as you go from the top of the group to the bottom of the group. So our lowest electronegativity will be rubidium, followed by potassium, then sodium, and lithium should have the highest electronegativity of that group of elements. As always, try out C and D on your own and check your work against the answer key. Let's finish up today's lesson just kind of summarizing the periodic trends and really comparing and contrasting metallic properties versus non-metallic properties. So when it comes to gaining or losing electrons, metals always lose electrons. Non-metals will always gain electrons. If we compare the size of the ionic radius, so the ion that's going to form, either cation or anion, versus the atomic radius, when it comes to metals, since they always lose electrons and form cations, the atomic radius will, let's make it consistent, the ionic radius will be smaller than the atomic radius. Since nonmetals always gain electrons, their ionic radius will be larger than the atomic radius. As far as atomic radius goes, our metallic elements tend to be pretty big. They're going to be the largest element, the largest atom within the period. As you make your way to the right and you get to more non-metallic elements, you're going to see smaller and smaller atoms. Ionization energy of metals tends to be very low. These are big atoms with their valence electrons far away from the nucleus, so they're not particularly attracted to the nucleus. They should be easy to remove. Translation, less energy to remove them. Non-metallics are going to have high ionization energy. Those atoms are small. The valence electrons are held pretty tightly, so it needs to put a lot of energy in to rip away an electron. Electronegativity is talking about how an atom will attract electrons to itself in a bond. Well, metals can barely attract their own electrons, so when bonded to something else, they have very weak ability to attract electrons to themselves. They will tend to have low electronegativities. Non-metallics, again, powerful nucleus, small atomic radius, they can attract their own electrons, and they're strong enough to pull the electrons towards themselves in a bond. Keep in mind that our noble gases, group 18, have no electronegativity values as they do not bond. If I wanted to find the quintessential metal, so really, really big with low ionization energy and low electronegativity, what corner of the periodic table should I be looking in? Hopefully you're thinking the lower left. In the lower left, we've got like cesium and francium. Francium is super rare, so cesium might be a more practical example, but that's like the most metallic behavior we can see. Huge atom with very low ionization energy and electronegativity. The polar opposite, it's kind of our best example of a nonmetal. So small with high ionization energy and high electronegativity. Hopefully you're thinking the upper right. But again, leave group 18 out of it. This kind of leaves fluorine as our most quintessential non-metal as far as its behavior is concerned. So just keep those two things in mind. The more you get to the upper right corner of the periodic table, excluding group 18 elements, the more non-metallic that element is. Lower left, the more metallic that element is. All right, sorry that was a long one today, guys. I apologize. Thank you for tuning in, and I hope you found this helpful.